Looking at the first page of the new set of practice problems, I'd like to explain how the octet rule leads to the formation of positive and negative ions for different elements. There's also a pattern to how these ions form, or the charges of these ions on the periodic table. So I've already started by labeling my periodic table with the group numbers along the top, and you should always have this on your periodic table. What I want to do as we go through is add in what are the ionic charges that each element gives rise to. The other thing to keep in mind is that Mendeleev, the person who's credited with designing the modern table back in the 1860s, organized elements in columns, right, what we call groups. All the elements in a particular column are chemically alike. So Mendeleev didn't know why beryllium, magnesium, calcium, strontium, and so on all behaved the same way chemically, but he knew that they were similar in their chemical behavior, so he organized them in the same group. Today, we understand what it is about them that makes them the same, and that is that they all have two outermost electrons, which corresponds to the group number. Having a certain number of outermost electrons makes the atom behave a certain way because all those atoms are going to try to complete their octet in the same manner, and that's what gives rise to their similar chemical behavior. And this is true of all the elements in all the columns. So if I go to the other side of the table and I look at, say, atoms in group 3, all of these atoms are alike because they all have the same number of outermost electrons, and they will form the same kind of ion. And similar for the other groups. Now, group 8, of course, is not going to make ions because they already have a complete octet. What would be the reason for pushing around electrons, right? It just doesn't make sense. So they are inert and they do not form ions of any sort. All right, so let's look at the problems. The first thing I want to point out is the pairing. Problems 1 and 2 are both about calcium. 3 and 4 are both about sulfur. 5 and 6 are both about iodine. And that's true for every row, both above the dotted line and below, except for 1. And that would be 11 and 12. 11 and 12 are individual atoms. And I only put them on the page to show you that I can ask questions about individual atoms. Every question doesn't have to be a pair. Now, the reason I did the pair is really twofold. I want you to compare what happens to the neutral atom when it becomes an ion. So you need to be able to see both. We sometimes call the neutral atom the parent atom because it gives rise to the offspring, which is the ion, either the positive or the negative ion. The other reason for the pairing is below the dotted line, I sort of hid the identity of some of the atoms. So in order to figure out what some of the atoms are and to figure out the ionic details, you needed to know some more information. And between the two problems in that row, there's enough information to figure out everything. So that's why the pairing. So let's start out by looking first at the same kind of ion. Let's start out by looking at the anions, the negatively charged ions, how they come about. So the first one of those would be 3 and 4. And before I actually draw the ion, I really think it makes the most sense to draw the neutral parent. So I'm going to start with number 4, which is just an atom of sulfur. So I know from my electron shell diagram work that there's 3 shells, there's 6 in the outer shell, and this is what the shells look like. We're also going to do iodine, right? So that's 5 and 6, but I'm going to do the neutral parent first, so that's number 5. Find iodine on your table. 1, 2, 3. Okay. So it's 1, 2, 3, 4, 5, 7, 2, 8, 18, 18. So here I have the shell diagrams of 2 neutral atoms. Now, why are they neutral? Right? Let's agree on that again. So we know that sulfur is neutral because there's 16 protons and 16 electrons. Equal amounts of opposite charge make you neutral. In the case of iodine, there are 53 protons, and if you add it all up, 53 electrons out in the cloud. So it also is neutral. So these atoms have a desirable quality, neutrality, but it's not the most desirable thing to an atom. Atoms are far more interested in a complete in a complete octet than neutrality. And this is easy to demonstrate because atoms will readily sacrifice their neutrality in exchange for a complete octet. So that's what we need to demonstrate now. So let's consider what happens for these two atoms. Neither one has a complete octet. You can see the outermost shell here is a 7 and a 6, and that's not working for the octet rule. So we'll start out with number 4. What could we do so that this atom ends up with 8 outermost electrons? Turns out there are 2 distinctive ways to make that happen. One involving the gain of electrons, and the other involving the loss of electrons. Now, where these electrons come from and where they go is not relevant for this particular unit. In an upcoming unit, we will talk about where these electrons come from and go to. So one way to get to 8 would be to add 2 electrons to the outer shell. That would bring us from 6 up to the magic number of 8. The other way would be to lose the 6 that are in that outer shell. If we were to lose these 6, then that shell would be gone. Electron shells only exist if there's electrons present in the shells. So that would make this the new outer shell with the magic number of 8. So theoretically, we could force either thing to happen. But what normally happens in our universe, the process that occurs is the one that's energetically favorable. That means the easier thing to do is the thing that happens, right? The same thing typically happens with people too. So that means of the 2 choices, it's easier to move around 2 electrons than 6. And that's what's going to happen. So our neutral sulfur atom is going to gain 2 electrons. So what does that look like when that happens? So now we're going to look at the ion. Well, we're going to go from the original shell structure, where we originally had a 6 in the outer shell, up to a total of 8, because 6 plus 2 is 8. And now we have an atom that seems to have a complete octet. This is very desirable to the atom. So in order to get there, we had to lose the neutrality. Why is this atom now a -2 ion? Well, let's consider the number of particles. There's still 16 protons in the nucleus, but now when you count up the electrons out in the cloud, you can see that there are 18 electrons. So what we notice is that there's an excess of 2 negative charges. And that's what makes this a -2 ion, and the -2 is written here as an exponent after the symbol. So on our periodic table, what we can do is we can go to the sulfur box, which is here. We can read up to the top of the column. It's in group 6, right? 6 outer electrons. And what did it do to complete its octet? It formed a -2 ion. Now, why am I labeling all the elements in that column -2? Because all the elements in this column, remember, are chemically alike. That's how Mendeleev set up the table. So all of these elements have 6 outer electrons and solve or complete their octet by gaining 2 electrons and forming a -2 ion. So not only should you label your table with the group numbers, you should also label them with the typical ionic charges that form in that column as well. Let's look at another set of problems. So 5 and 6, iodine. So my iodine currently has 7 outer electrons. That's not good. It wants to have a complete octet. So we know there's 2 ways to get there. One that involves the gain and one that involves the loss. We could add 1 electron or we could lose 7. The easier thing to do is to add the 1, the fewer number of electrons. So that's going to change what our shell structure looks like. So now we're going to have 1, 2, 3, 4, 5 shells, but the important thing is now the outer shell is going to be at 8. All the other shells are going to be exactly the same, right? They're unaffected. When you do the math, you've got 53 protons and now 54 electrons. And because there's an excess of 1 negative charge compared to positives, this is why the ion is a -1. On our periodic table, we should go to iodine. Here it is. If we know what iodine does, then we know what all the elements in this column does. They all form ions with a -1 charge. All right, so that was two anions. And before I move on to the cations, I want to point out a consistent behavior. These two atoms made their ions the same way by adding electrons to the outer shell. They started with a certain number of shells and they end it with the same number of shells. Now that's in contrast to what you're going to see the cations do right now. So let's look at those. So we'll start out with calcium. So looking at the calcium, we should start with the neutral parent. That would be number 1. We've made this diagram before. There you have it. Neutral because there's equal numbers of positive and negative charge. But it doesn't have a complete octet. So how do we solve that? Well, there are two distinctive ways of solving that, same as for the anions. One that involves the gain of electrons and one that involves the loss. We could gain 6, that's theoretically possible, or we could lose the 2. Of course, what's easier to do is to lose the 2. If we lose these 2, we end up with a new outer shell that has the magic number of 8, and this would be your complete octet. So the shell structure here now looks like 288. We have a complete octet. But why the charge? So we started with 20 protons, and now when you count them up out in the cloud, we only have 18 electrons. So now there's an excess of positive charge. There's an excess of 2 positive charges, and that's why the charge is now positive 2. So on our periodic table, we have calcium right here. It's in group 2. All those elements do the same thing and form ions with a positive 2. So how is this different from the anions? Look at the different solution to the octet rule. Instead of adding electrons to the outer shell, we got rid of the outer shell, right? We emptied it, and we were able to then establish a new outer shell that had the magic number. Let's look at this one more time with 9 and 10. So of course I'm going to do 10 first. It's an atom of aluminum. What does aluminum do to complete its octet? Well, there's 2 possibilities. Gaining, losing. Lose 3 or gain 5. Of course, we're going to do the easier of the 2. We're going to lose the 3. And when you lose the 3, you lose the outer shell, and that leaves you with 2 shells where the outer shell now has the magic number. When you count up the protons and the electrons, you see why the charge is positive 3. So let me go to our table and update column 3, because now we know that this always forms a positive 3 ion. And you could do this process really anywhere on the table and figure out the corresponding charges of all the elements in that column. So we didn't do any examples from group 1, but if you were to, you would find that they form positive 1 ions. So now it's positive 1, positive 2, positive 3. Group number 4, let me skip over that for a moment. And then I have group 5, negative 2, negative 1, and nothing. You know, this unit is about patterns on the periodic table. This is a negative 3. And if you were to diagram any one of these atoms, you would see why they form negative 3 ions. So this just leaves group 4. The issue with group 4 is that does it gain 4 electrons or does it lose 4 electrons? Well, it turns out that each process is energetically favorable over the other. You could gain 4, you could lose 4, they're really equivalent. So these atoms could go either way. That means they're either going to be a +4 or a -4. Both are possible. Now, how are you going to know which one it does? Well, honestly, that is dictated by the other guy. Now, what I mean by that will be discussed in the next unit. So for now, you could literally choose either +4 or -4. It's really not going to matter. Now, this does leave one set of atoms with sort of unknown ionic charges, and that would be the transition metals in the center of the table. See, because we didn't label these, we didn't number these with a group number. So you'll notice the color coding. Because of electron configuration, all right, and Hund's rule, these atoms here mostly have two outer electrons. In fact, the unshaded boxes have two outer electrons. So you would expect those to form positive 2 ions, of course. Then you have the shaded boxes, like this one right here. And these shaded boxes have one outer electron. So you would expect these to form positive 1 ions. And this only leaves one more box, and this box is very unusual, and that's the palladium box, this deeply shaded box. And this actually has no outermost electrons. So I alluded to this possibility in an earlier video. No outermost electrons, what the hell? How could this be? There has to be some electrons that are furthest from the nucleus than the rest, and of course there are. But it takes something extra to be an outermost electron. Outermost electrons aren't just the farthest out. By definition, outermost electrons are typically s and p electrons. Now that only makes sense if you engaged with me with the electron configuration lesson. If you didn't, honestly folks, you don't need to worry about. But outer electrons always come from s and p. And just briefly, why would that be? The tall columns, right? These here on the left and these here on the right, you'll recognize are the S and P blocks when you use the block method of the table. And how do you get to the magic number of 8? Well, if you took the S electrons and the P electrons, just think about this. S electrons, you could only have 2 of them. P electrons, you could only have 6 of them. And what does that add up to? That adds up to 8. And there's really no accident about that. That is totally relevant to the octet rule. But honestly, just outside the scope of our course. All right, so that's the top of this page, all right? What I suggest you do is finish the rest of the problems, look at your periodic table, make sure your labeling is done, make sure you understand how to take a neutral atom and use it and the octet rule and form its corresponding ion. Then come back for the next video and I will talk about the detective work at the bottom of this page.